Welcome to the module Enthalpy. In this module, we introduce the physical quantity of enthalpy as well as explore its temperature dependence and its relationship with internal energy. Most experiments in chemistry do not take place at constant volume, but rather at constant pressure. With this in mind, we are looking for a function whose change is equal to the heat added or removed at constant pressure. This function is enthalpy. Enthalpy H is defined as the sum of internal energy U plus the product of pressure P and volume V. As U, P and V are state functions, so is enthalpy. Additionally, because U and V are extensive state functions, enthalpy is extensive as well. Let's explore the connection between the change of enthalpy and heat exchanged between a system and its surroundings. We will only consider compression or expansion work done on or by the system and neglect all other types of work. The differential of enthalpy is equal to the differential of internal energy U du plus P times dV plus V times dP. We can express du via the equation for the first law of thermodynamics, with work being equal to the negative of P times dV. Here we focus on the equilibrium conditions and assume that the external pressure, which should normally be here, is equal to the internal pressure in the system. After this substitution, the resulting expression for dH becomes delta Q plus V times dP. At constant pressure, the infinitesimal change of enthalpy, dH, is equal to the infinitesimal change in heat, delta Q. The subscript P in the expression QP denotes that the heat exchange between the system and its surroundings occurs at constant pressure. Just like with internal energy, we can introduce a heat capacity for enthalpy. This quantity, Cp, is called heat capacity at constant pressure. It is the derivative of the heat exchanged at constant pressure with respect to temperature. This time, this derivative is taken along the path of the constant pressure. As we have seen, the heat exchanged along this path is equal to the change in enthalpy of the system. Hence, this quantity is equivalent to the partial derivative of enthalpy with respect to temperature at constant pressure. The heat capacity at constant pressure is an extensive system property, while molar heat capacity at constant pressure is an intensive property specific to a system or substance. We can also consider enthalpy H as a function of two variables, T and P. The total differential of H shown here summarizes the dependence of enthalpy on temperature and pressure. The temperature dependence of enthalpy at constant pressure is given by the heat capacity at constant pressure, while the pressure dependence of enthalpy at constant temperature is given by another term. The second term should be in general taken into account, but we will not explore it. In the special case of the ideal gas, enthalpy can be represented as U plus nRT. This means that for an ideal gas, enthalpy depends only on temperature, not on pressure. What is the physical meaning of enthalpy and how does it relate to internal energy? There are some key relationships to consider for processes at constant pressure. Let's look at the following example. When we heat a system reversibly at a constant pressure, the change in enthalpy, delta H, is equal to the added heat, Qp. Using the first law of thermodynamics, or the definition of enthalpy, this can be broken down further. This heat and delta H are also equal to the sum of the change in internal energy, delta U, and the work done by the system during its expansion, which is represented by P delta V. This relation is particularly simple in the case of an ideal gas. For an ideal gas, this work of expansion can be replaced by the term nR delta T, where delta T is the change in temperature. This example can be generalized as follows. For processes at constant pressure, the change in enthalpy combines both the change in the system's internal energy and the work done during its expansion or compression. Elaborating on the connection between enthalpy and internal energy, let us now look at the relationship between two parameters describing temperature dependence of internal energy and enthalpy, CV and CP. There is, in fact, a general equation that reveals this connection, but we will not study it. Instead, we will focus on two specific and significant scenarios. First, let's consider condensed phases. By condensed phase, we mean either solids or liquids. A distinguishing feature of these phases is that as one changes the temperature at a constant pressure, their volume don't change much. In fact, for most practical purposes, we consider such volume changes to be negligible. This implies that for condensed phases, Cp is approximately equal to Cv. The two heat capacities are almost the same because the system doesn't do much expansion or compression work as it heats up or cools down. Now, what about ideal gases? The relationship here is different but still rather straightforward. For ideal gases, the heat capacity at constant pressure, Cp, is equal to the heat capacity at constant volume, Cv, plus a term Nr. Breaking this down further, for molar quantities, we can represent this as Cpm being equal to Cvm plus the universal gas constant R. Now we would like to present a visual illustration of the concepts we have just covered. On this graph, you see how both enthalpy and internal energy change for gases as temperature increases. It is evident that enthalpy rises slightly faster than internal energy. The slope of the tangent at any specific point on the enthalpy curve represents the heat capacity at constant pressure Cp. For the internal energy curve, this slope corresponds to the heat capacity at constant volume Cv. Given that Cp accounts for both the change in internal energy and the work performed during the heating of a gas at constant pressure, Cp is larger than Cv. This distinction explains why the enthalpy curve has a slightly steeper incline compared to that of internal energy.